Okay, I believe we're ready to start our webinar now. My name is Kathleen Bensko. I'm the senior geologist with the Federal Energy Regulatory Commission, and I'm also the co-chair of the DFI International Grouting Committee. My other chair is Raffaella Granata from Italy, and she also works for Trevi. So our webinar today is, I lost my screen. There we go. Sorry about that. Our webinar today, we are featuring 3 presentations. And this is our second webinar that we're holding. The first one was held earlier in the summer. And what we will be doing, our International Grouting Committee will be sponsoring 2 other webinars coming up in 2025. One will be in July and one in December. We hope that you'll be able to join us. We also will be holding our DFI Committee Week. It's coming up in April the 28th to May 2nd. So I'd like to go ahead and welcome everyone again. I hope you enjoy our webinar. The rules of engagement will be during the webinar, all attendees will be muted. We will hold a Q&A session that will follow the very last presentation. So we're just going to run straight through all 3 of them. And please put your questions in the webinar chat. And when you do, please reference which speaker your question is directed to. That way, it'll make it easier for us to get your answers to you in a timely manner. Our speakers today will be Billy Fisher. He will be up first. His presentation is When the Tunnel Meets the Railroad, a Grouting Case History. Currently, Mr. Fisher is the division manager of Russo Corporation's Foundation Western Division. He has 2 decades of geotechnical construction experience, providing pre-construction, estimating, business development, project management, and operations management. His experience in deep foundations includes auger cast piles, micropiles, helical and drilled shafts, as well as earth retention, compaction grouting, low mobility grouting, high mobility grouting, railroad subgrade injection stabilization, and multiple ground improvement techniques, including vibro piers, compaction grouting, jet grouting, soil mixing, and injection systems. He has, and also, injection systems for expansive clays. Our second presentation will be with Mr. Jose Torres and Mr. Conrad Ginther. Jose is a project manager at Nicholson Construction Company in Canonsburg, Pennsylvania. Mr. Torres is an expert in dam foundations curtain grouting. Mr. Torres has jointly published a paper called Drilling and Grouting with Exclusive Use of Instrumented Packers at the Boone Dam Internal Erosion Mitigation Project. This paper was for USSD. He completed a bachelor's degree in civil engineering at the NYU Tandon School of Engineering in Brooklyn, New York. Mr. Conrad Ginther is a principal engineer with Geosyntec, focused on design and implementation of specialty geotechnical construction, including post-tension anchors, drilling and grouting, cutoff walls, and composite barriers, and is experienced in the design and construction of gravity concrete dams and their appurtenances. He has extensive experience with best practices in dam safety and has participated in numerous dam safety inspections, PFMAs, and SQRAs for projects regulated by the FERC, USACE, TVA, and other federal and state agencies. Mr. Ginther has experience as an engineering consultant, contractor, and owner's representative on high-profile projects in the United States and also internationally. Our third presentation by Eric Manning is on the Logan Martin Dam Deep Grouting Project update. Eric Manning has served as the Geostructural Services Supervisor in the Hydro Dam Safety Department for Southern Company since 2014. At Southern Company, Eric designs, manages, and consults on remedial grouting and geotechnical projects for Southern Company's subsidiaries, Alabama Power and Georgia Power. His primary focus is supervisor of the Logan Martin Dam Deep Grouting Project. He is a member of the DFI Institute for International Grouting Committee and grouting. He's also on our subcommittee, Grouting Materials and Methods. Eric has a BS degree from Auburn University and is a professional engineer registered in the state of Alabama. So with that, I hope you enjoy our webinar today, and I will hand it off now to Billy Fisher to start.
All right, thank you. This is to be just a case study on a grouting project for a tunnel. The project involved a new 36-inch water main that was going to connect the north and south water systems around Metro Birmingham, and a portion of that was going to be a 60-inch steel encased tunnel that was going to go beneath an existing railroad track. We're just going to go over the history, some of the plans, the geology, kind of what we encountered, and then the grouting program that we had to develop and then go and execute. The project is just on the east side of Birmingham, and here is the section that's going to go under of the pipe that got tunneled that was going to be under the Norfolk Southern Railroad line. Obviously, this the rest of the tunnel was going to be open cut, or the rest of the pipe installation was just open cut, but the part under the track is the one that had to be tunneled. The overall project was 365 feet of water main. 120 feet of that was going to be 60-inch steel cased, and it was going to be a jack and bore tunneling method originally. This is the 120-foot section that was going to go under the existing rail line. Like I said, in that zone, there were approximately 3 borings that were done, and you can see the tunneling is relatively shallow. It's a relatively shallow tunnel, approximately 13 feet below the rail line. That's how much overburden there was over the proposed tunnel. And you'll notice there was some construction debris in the borings, but mainly it was just in the upper 5 feet. So the tunneling people weren't too concerned about that based on the borings. It wasn't until later that we ran into the excessive amount of brick that was in the tunnel. The casing was going to be hydraulically pushed, and then the face was internally auger mined. Like I said, there was a lot more brick that was anticipated than based on what was provided in the borings. There was a concern that as the face become unstable during the jack and bore, it could potentially cause some issues with the existing rail line. So tunneling was paused, obviously, and then we did some exploratory pits to find the extent of the debris. So based on the observation pits, you can see the stacked brick. It was a very uncontrolled fill under the railway, but all within the railway right of way, which is where the 120-foot section of tunneling was going to take place. Only about 60 feet of that was affected by the backfill. So it was determined on site that we'd have to stop the tunneling, come up with some options, to figure out a way to get through this. Two options were evaluated. One was just to lower the tunnel alignment to pass under the fill through the lower rock formation. That would have involved creating a deeper access shaft. So we'd have to put more shoring in, lower that, and then, bring the tunnel down deeper and then bring it back up, along with the cost associated with the additional piping. And then the other option was we discussed going in, grouting the brick and soil matrix. So then the tunnel it would lock all that material together, and then we could go in and they could continue the tunneling operation. So to do that, we had to create a grouting program. So once we had selected grouting, we created a grouting program. We had to determine, okay, what's the best option, and what type of grout did we want to use? Whether that was going to be a cementitious grout or like a polyurethane grout, or even like a compaction grout or a low mobility grout. Based on the potential for large voids and the need to tunnel back through the grouting material, we opted for a cementitious grout. Then we had to develop a mix design that would be appropriate to lock the matrix of soil, but also it had to be weak enough so that the tunneling contractor could then come back and tunnel back through that material, because we were going to be grouting the entire profile of the tunnel as well as all of the soil above the tunnel. And they were just going to use conventional tunneling methods. They weren't using a boring machine or anything like that. They were just jack and boring originally. How are we going to introduce the grout into this soil matrix was one of the things we had to determine, and I'll go over, ultimately what we decided to do. What was going to be the grouting criteria we would use in the field, to ensure the zone had been properly grouted. Because ultimately that was the main goal, is we had to get this zone grouted so we could tunnel back through. We didn't really have the option of this not working, because we had proposed both options and we selected this one. And we had to be able to make adjustments in the field, like with any grouting program. You can sit and sit around, determine this, come up with the best option, but it has to be flexible enough that when you get into the field, you're going to have to make changes typically. And since we were working under another owner, we were working for the city of Birmingham. We were just tunneling under the railroad track, so we had to submit all this for their approval, but we had to make it in a way where we could adjust it on the fly, not have to stop, go back to the railroad, make a change. So that was important to us as well. We opted for a microfine cement. We ran a few different mixes in the lab just to determine what would be the best option for us. We ran a 2-to-1 water cement ratio, a 2.5-to-1 water cement ratio, and a 3-to-1 water cement ratio. We were looking at ultimately, how much was the mix going to bleed? What was the bleed percentage, and what was the strength? We had opted for, we were targeting like 200 psi for the grout. We figured we just needed to be strong enough to lock all the material together, but also be weak enough where we could tunnel back through this. And then we wanted to limit the bleed to less than 2%. So we used a Master Builder, Master Rock MP650 microfine cement. Obviously had water in the mix, and then we used a high range water reducer, as well as Dietin gum. I lost my notes. And then we also had Delvo just to control the set. So the Dietin gum was what we used to control the bleed. In many of your applications, you know, that are under pressure, you don't want to. We're trying to keep the water from separating from the mix because we're pumping into a mass. This is especially important here because we weren't sure if what type of voids we would encounter, if they were larger voids. So we needed bleed to be stable for the grout, so they would uniformly suspend until the grout was able to set, and everything would be uniformly distributed into the void space. Um, you know, grout stability can be described in two ways: through bleed, um, and then Dietin gum was a sugar byproduct, which means is, you know, we had to be careful we didn't overdose it as well because it can adjust the set time. Um, the Dietin gum was a powder, so we had to mix it with water to make it into a gel prior to adding it to the mix. Some of the results from the mix design. So mix one in the lab, we had, you know, on confines of about 260 psi and roughly zero bleed. Mix two, similar breaks, but we had a greater amount of bleed. And then mix three, we just determined it was not really going to be an option because the bleed was greater than 3%. And then also they had difficulty removing the samples from the molds. It was just not setting. It just was too high of a water cement ratio. So we had to develop a work plan. We decided we would go with 4 rows of grout holes. They were on like a 2.5 by 2.5 grid. And then because of the track, we were limited to how close we could get to the track based on the right of way because this was an active rail line. So as you can see, we had vertical holes and we had battered holes to get to the zone that was below the track based on the project constraints that the railroad placed on us. This is just kind of, we used a medium-sized drill, a C5, to drill in the grout pipes. We drilled the holes down to the top of rock, so we were pretty much grouting from the rock formation all the way as close to the surface as we could. We used 73 millimeter drill pipe, and we had custom built step drag bits that were machined to the exact diameter of the 73 millimeter pipe so that we could not create too much of an annulus around the pipe during the pipe installation, because we wanted to try to make sure we didn't get early grout fusel around the pipe. We used rotary air flush, you know, to get the pipe in, but we were very minimal on the amount of air we used, just enough to get the tooling down to the top of rock. And then we grouted through the rig and the tooling through like a grout swivel on the drill head. Here's the pipe, and you can see the different batters on the pipe in the field. So it was obviously made, you know, grouting a little bit complicated, but that was, like I said, just due to the railroad requirements. But so we used a Kim grout machine to batch. Typical batch was, we used the microfine cement, they were 44-pound bags. And so we were batching 3 bags at a time, you know, 31.5 gallons to 132 pounds of microfine cement. And then we were adding 900 grams of real wheel 1000 and 44 grams of the Dietin gum to control the bleed. And that was, like I said, pre-blended with water to create, it's like a gel material. In the field, we were getting of the mix a specific gravity of 1.25, which was very similar to the lab results that we were getting on the mixture as well. So we set up a primary and secondary sequence across the holes. We started with the outer two, line A and D, and we grouted those in a primary and secondary fashion just to create some confinement. And then we would come in and do the interior rows B and C, on every other pattern as well. So the grouting criteria, how did we determine that we had grouted everything properly? So, we were going to grout from the rock to the surface. We did grouting in 2-foot intervals. We were grouting every 2 feet. We would grout, and once we hit our cutoff criteria, we would come up 2 feet, and so on and so on. We just determined that we would do it based on, we were shooting for 100 psi. It's a flow of about 100.5 cubic feet per minute for 10 minutes. And then, or if we had refusal, a ground refusal, or communication with another location was another one of the criteria to stop grouting. Or if we hit a ultimate pressure of 200 psi. But if we didn't meet the criteria, we really had no volume limit. Because we were trying to make sure we filled all the holes as long as we didn't have refusal. And then once we got the refusal, we would go to the next stage, and so on and so on. Once we were going, we decided on the initial primaries, we made a change in the field. We set a volume cutoff just on the outside primaries of like 75 gallons per zone, so that we could try to limit how far the grout was traveling outside of the zone that we were trying to grout. So we did set volume criteria on just the outer rows, and then we didn't on the inner rows ultimately. So that's when I was talking about we have to be able to have a flexible grouting program. We did field testing on just on the grout to make sure, because obviously we were concerned with strength. We want to make sure in the field we weren't creating a stronger grout or a weaker grout, and that because down the road it would potentially be an issue for the guys doing the tunneling. So our 14-day average was 255 psi, and then our 28 was actually slightly less. Not really sure what led to that ultimately, other than they were very low strike samples, and I don't know if that was more had to do with the curing of the grout or maybe in the handling of the grout. But I know that some of the samples, they were damaged because it was difficult to get the sample out of the mold. We actually had to go to the testing lab just to help them with that. We talked to Master Builder just to see what they recommended. So we had come up with a plan on how to get the samples out without damaging as few of those as possible. Ultimately, this process was just to facilitate the tunnel installation. There wasn't like a contract specified design strength. So ultimately, the fact that it was less at 28 days, it was really just there to get the tunnel in, and then that was the ultimate goal. This is just some modeling that we did, kind of as a project was going, just to kind of see kind of where we could see kind of where the grout was going. Obviously, this isn't an exact representation of what we did in the field because we really don't know, but it's just, these are just representing volumes at depth just to get an idea of, how everything was going, and where we needed to, and if we needed to install tertiary holes, which we did install a few tertiary holes where we had very low grout takes. As you can see, the battered holes, I mean, that was probably the hardest part, was just trying to grout the really steep battered holes. for the project. And then this is the tunneling contractor. I mean, you can see now they were literally just hand excavating the remainder. That's how they opted to complete the tunnel after the grouting was done. Thanks. Now I'm going to turn it over to Conrad with Geosyntec and Jose with Nicholson to talk about their presentation.
Thank you, Billy. I appreciate that. Why is the video not starting?
There you are.
Yeah. Thank you very much. We're going to talk about type 1L use in dam embankment or in dam foundation grouting. We're going to talk about, what is 1L cement, typical observations that we have in the use of, typical cements, which is type 1, type 2, 3, and then how we're using type 1L on other projects, and sort of how they compare with fresh properties. Of course, this is the disclaimer. There's going to be some opinions in here, so take that with a grain of salt. So this is here on the right, you have a little bit of a diagram. If anybody asked you during Christmas dinner, how cement is made, you can pull this one out of your back pocket. So, they take raw material, they crush it, mill it, turn it into a raw mix. It goes into a kiln. They turn it to clinker, they cool it down, they grind it, and voila, we have cement. If you didn't know. So typically, that whole process, for every 1 ton of Portland cement, clinker that you make, it generates about a ton of carbon dioxide. So there's a big sort of greenhouse effect, I would say, of creating this Portland cement. So what's going on is in the world today, there's lots of companies, world governments, private companies, they're just demanding low carbon energy sources and things that are climate friendly. There's things like that's the Buy Clean Act just worldwide. In the US, I believe we have something called the Clean Future Act, and we'll see what goes on with that. But basically, it's requirements and incentives to reduce emissions of greenhouse gases. And they want to reduce greenhouse gases by 50% of where they were in 2005 by 2030. And they want to get to net zero by 2050. And then there's some countries now that are actually applying carbon taxes for creating all this carbon dioxide. And so that a country that comes to mind is Sweden. They will tax you $139 per metric ton of carbon dioxide right now, if you're a cement company. So there's different types of cement, blended cements out there that are used worldwide for the reduction of the carbon footprint. The one we're going to talk about is type 1L. So that means type 1L generally uses ground limestone as a replacement for some of the cement content. That's usually within 5 to 15%. There is type 1P, which is substitution of pozzolans up to 40%. 1S is slag up to 95%. And then there's type IT, which is basically the mixing all of those things together to try to reduce that footprint. Let's see. So I already talked about this. So ASTM C595, type 1L is 5 to 15% grind limestone. They recommend that you use it basically in a 1-to-1 replacement. So if you're using type 1 or type 2 or type 3 or even type 5, the way that you're using it, they make it real simple. It's like, hey, just put the same amount of type 1, 2, 3, 5 that you were using in your mixes and replace it with 1L and then see what happens, right? Using a like for like manner. One thing that I've noticed, and the reason we're having this, we get a lot of bids or a lot of proposals out, and everybody's sort of copying these specs and saying, hey, use type 1, use type 2, use type 3, use type 5. But these things are getting harder and harder to find as companies move away from making them. So nobody wants to be the first person to use type 1L, but somebody has to be. I'm not saying that we are the first people, but certainly there needs to be more discussion and testing around 1L, right? And yet I also have to say this: stop copying specifications, please. All right, I had to do it. I know Conrad's next to me; he's going to hit me, but I have to stop copying specifications. So we're going to look at 4 different jobs. The first one was Boone Dam. We used a type 1-2 cement, Portland cement. On that job, we had 5 high mobility grout mixes. These are balanced stabilized grout mixes. That means, little to no bleed, reduced pressure filtration. I put the mill certs for that cement here on this slide. This mix had about 2.5% grind limestone content. So I'll just say typical cements before this 1L came through, they allow up to 5% limestone content generally. But in the mix also was bentonite slurry. At the time for this mix, we used whaling gum as a viscosity modifier and to help control bleed as well. Master Real Build 1000 and water in the mix. And the other job we're looking at is Chimney Hollow. There was about 4 balanced stabilized grout mixes. That was using type 3 Portland cement. I had a limestone content of 3.7%. Mix very similar here. The only thing is we switched out whaling gum for dieting gum, just really for availability purposes, and dieting gum's a little bit more robust. Sulaks, we did this job the first time we used type 1L at 15%. So in fact, when you see type 1L, that number in parentheses will tell you how much limestone content is in your mix. Okay, but that job had 3 balanced stabilized grout mixes. So using 1L Portland cement, that has a 15% ground limestone mix. Generally, the mix components were the same as the other 2. And then for Red Bluff, where we are currently, we're using type 1L cement with a 10% ground limestone content. And we're using about 3 mixes here. The funny thing is the specification actually required the use of type 5 cement. And we asked for a variance. Well, it asked for type 5 because it was high chloride and sulfate content in the soils and in the groundwater. So the mix had to have some sort of high sulfate resistance. So we found and sourced the type of 1L cement, this type 1L10 that we're using, and it passed testing for high sulfate resistance. So we asked for a variance, and we're using 1L here on the job. These are just key features comparing all 4 of the mill certs we have for those cements that we used. So you can tell the difference in the limestone content, 2.5, 3.7, 15, and 10. Some comparisons for blade fineness. There's a lot of interest in blade fineness and what that means in terms of grout travel and maybe a little bit of segregation. I don't know if you want to call it that, but how it interacts with pressure filtration is something that we're going to be looking at in the future. I'm sure I've heard it from multiple people in the industry now, so there's big interest there. Here's some initial set times as well of every cement that's out there, based on the manufacturer recommendations anyway. And then there's some strength information for 3-day, 7-day, 28-day on what you can expect out of the cement to start with. And generally, we can see that the type 3 had the highest strength here on this table, followed by type 1-2. And then we have type 1L10 and type 1L15. I didn't put it in order, but that's sort of the order that the paperwork says it's going to be, right? So I did my best to compare mixes based on viscosity range. I will say that all these mixes in general are 1-to-1 mixes in terms of water cement ratio. It's a specific gravity of about 1.5. So here we're comparing set times. So in the 35 to 45 second range, basically the 1L15 took the longest to set. It's colored in orange. I don't know if I have the laser. colored in orange here. And the type 3 took the shortest amount of time to set in the 35 to 45 second range. When we get to the 45 to 55, our 1L10 seemed to take the longest. And again, type 3, shortest time. And then greater than 55 seconds, we're back to the 1L15 having the highest set time. And again, the winner, type 3, setting faster. It's not really a surprise. Type 3 is supposed to set faster. It's high early strength and high set times generally. But we did see, the longest set time for us was 16 hours. And that's a big question in the grouting world, because, unless you're doing 24/7 grouting, your work is kind of dictated by when the grout has set in the hole that you're working on, right? Or the foundation that you're treating. Like when that's set, you're allowed to keep drilling or moving next to adjacent holes. So 16 hours is quite a bit of time. So we did explore what using a non-chloride accelerator would look like. So we got that accelerator from Specrete, actually. And we saw that we were able, for our mix A at Red Bluff, which had an initial set time of 14.5 hours, we were able to get some set time gains by adding varying amounts of accelerator. So at 0.5%, we gained 2.2 hours. At 1%, we gained 3.6 hours. And at 1.5%, we gained 4.8 hours. So quite a bit of gain with the use of the accelerator, but we do start seeing some sort of diminishing returns as we add some more accelerator. In the end, I will tell you, we did not use it full time at Red Bluff, only because we get 120-degree weather all the time, and we're using chillers and we're using all sorts of things to keep our mix cool, and we're just using accelerators in that kind of conditions could get dicey if things break down. So we didn't opt to use it, but this is good news for those of us looking to get that set time down. All right. In terms of compressive strength, not really a surprise here, but in the 35 to 45 second range, type 3 had the highest unconfined compressive strength when we broke them. The lowest was the type 1-2 here, which is a little bit weird, but generally the type of 1L cements acted similar in the 35 to 45 second range. At 45 to 55, again, type 3 is the winner there. Not the winner, but just the highest strength, if you care. Looks like 1L and 1-2 performed pretty similarly. And then at 28 days, we did see that the 1L had the lowest strength at 20, and that had the 15%. The 1L with 15% had the lower strength. This one mix here in the 35 to 45 seconds is actually outside of that 1-to-1 ratio I was talking about. This is probably why this is so low. Your cement content will do a lot for strength. And trying to compare apples to apples as best as we can. But generally keep that in mind that, how much cement you have in there will change your strength and your set times. And in terms of pressure filtration, we saw that basically at the 35 to 45 second range that the type 1L10 had the lowest filtration. Pressure filtration coefficient for that was the lowest. 1L15 was higher than the type 3, and then the worst performer there was the 1-2. 45 to 55 second range, it's funny, we got very similar results across all 4 mixes. But it looks like that pressure filtration was less at the 1-2 and the 3 mixes. And then once we get to 55 seconds or more, the 1, 2, and 3 behave very similarly. And then we got a little bit more water squeezed out of the 1L10 and the 1L15. And that was interesting. We're going to look at that some more. It's kind of, you expect these values to sort of go down, but they kind of came up from the 45 to 55 second range. And that only happened really with the 1L mixes. So there's something to look further into as we look at pressure filtration with the 1L mixes. They're behaving a little bit oddly once we start to get at higher viscosity ranges. And then in terms of bleed, I was going to graph out the bleed, but honestly, we got bleed to 0% on all the mixes. You can really control bleed really easily with Whalen or Dieting gum dosages. So I didn't want to just show you guys a blank, some blank graphs. But this is pretty easy. There wasn't much of note in terms of bleed. And really, in terms of the key differences we observed, you know, the more limestone content that you have in your mix, generally we see higher set times. Of course, you can control that with accelerators. I think there's some good data there. We also saw that type 3 had the highest compressive strength breaks. And if you go back to the table where we compared the mill certs, that was kind of expected from what the manufacturer's recommendations were saying. Type 1.2 was very similar to type 1L in terms of compressive strength. And type 1L at the 15% content saw the lowest compressive strength. I'll be with you in a second. Lower pressure filtration values we saw at type 1, 2, 3 in general. And then type 1L 15, we did see a decrease in pressure filtration performance as the mixes became less fluid. And then a happy accident, not happy accident, but the way, you know, happy that we were able to get high sulfate resistance at a type 1L10, which was able to take the place of type 5 at Red Bluff. So, you know, there's uses for this type 1L mixes here as we move into everybody basically making it and getting away from type 1, 2, 3, and 5. And that was really all I have for you. So I am going to turn it over to Eric Manning over at Southern Company.
Thanks. Let's see. Let me back up. All right. So I'm going to be providing an update on the Logan Martin Deep grouting project. For those of you unfamiliar with the site, Logan Martin is located roughly in central Alabama, and it's a earthen embankment and gravity composite dam. Right here, you can see a few of the main components of the dam, and I'll kind of go through these going from left to right. You have the west embankment, which geologically varies slightly from the east embankment. Logan Martin was constructed on a karst geology. The west embankment has less fracturing and solutioning features. And then moving towards the right here, you see the concrete gravity section of the dam, and then the 77 bolster, which overlays the original riverbed section of the Coosa River that was inundated to develop Logan Martin Dam. And then you have the 79 bolster, the surcharge, the east bolster, which was just constructed back in 2019, and then the far east section of the embankment, which has had, through the history of the grouting programs at Logan Martin, has had little to no remedial grouting in that section. So as I mentioned, Logan Martin is constructed on a karst geology, located in central Alabama. And this figure here shows its geological location in relation to some other notable grouting projects. It's very similar to Boone Dam. Logan Martin is underlain by the Knox group, which is composed of dolomite that contains varying amounts of chert inner beds and the occasional limestone bed. Let's see if as you can see here, the rock at Logan Martin has undergone extensive faulting and folding, which has increased the development of the solutioning and other karstic features. It's resulted in the development of seepage paths that have developed along the stratigraphic zones and joints, at folding axes and faults. The solutioning has penetrated down pretty deep to depths around elevation 0, which Logan Martin, the crest, is around elevation 487.5. So there's been some drilling that's gone as deep as 600 feet or so below the crest elevation, and the solutioning features, the karst geology, doesn't have an end to its depth from what we've experienced out here, which makes it the remedial options limited. So without a end to the karst features, there is no bottom to grout to install a cutoff wall. So what we've been limited to through the years is what we refer to as a hanging grout curtain, which I'll kind of get into a little bit when I go through the various remedial grouting programs that's been performed out at Logan Martin through the years. So these karstic features resulted in karstic features and a deficiency, and what I would call a deficiency in the construction of the original grout curtain, which I'll also cover in the next couple of slides, resulted in the infamous 1968 sinkhole event, which you see here, nearly led to the uncontrolled release of the reservoir. You can see here on the cross section view of the sinkhole, nearly 80-foot chimney sink down to the filter and top of rock in that riverbed section of the dam. Let's see. Here we go. All right. And just a timeline of major milestones throughout the years at Logan Martin. Subsurface geotechnical investigations began in the mid-50s, and construction began in the 60s with the original grout curtain. Then there was very little to no grouting efforts after the original grout curtain until the 1968 sinkhole. And the 1968 sinkhole triggered the programs that you see here in the 70s, which I refer to as the era of exploratory grouting, and I call it that because there really wasn't a structured grouting program with a clear, definitive goal. They just identified areas that were geologically significant that may have weak points in the original grout curtain. The grouts that were used in the original grout curtain would be considered unstable and erodible. And during that era, from roughly about 72 to 77, there was approximately 80,000 linear feet of grout holes and 194,000 cubic feet of grout that had been injected in about 456 holes. At that stage in the program, deep leakage wasn't of a lot of concern at the time, because it wasn't considered a risk to the dike's stability. So for that reason, A through D lines were only grouted down to to roughly about 100 feet into rock. But in later years, and as those grouting programs progressed, we noticed that there was a lot of piezometric responses on relatively deep grouting, which led us to see that the permeability of the rock and its hydraulic conductivity connected relatively quickly and shallow, and piezometers that were relatively close upstream. So this led to us extending the grout curtain much deeper to what we do now. A lot of the work that I've done in the past 10 years at Logan Martin has been extending the grout curtain down to elevation 0. So taking it down from 100 to 150 feet, which was really originally installed on the A through D lines, to now where we go 475 feet down elevation 0. So as I mentioned, the original grout curtain I would consider to be pretty deficient for these reasons. The primary holes originally in the test section prior to the construction of the embankment, prior to it commencing, the criteria or the design for the test section was on 20-foot centers, and then the volumetric criteria was 0.5 cubic feet per linear foot to achieve closure. And through what appeared to be reading between the lines in the old reports, Alabama Power faced extraordinary budget constraints and schedule constraints with the scheduled project, or the scheduled construction to start in early 1961. And so they basically reestablished the guidelines for installing the original grout curtain, and based on inconclusive results from the test section, they doubled the spacing of the primary holes, and then they doubled the volumetric refusal criteria as well. As well as that, as I mentioned, the grouts that they used in the original grout curtain were erodible. They were as much as 9 parts limestone rock dust to 1 part cement. And there was a lot of fly ash as well. So following the 1968 sinkhole in the 70s, you see A line through D line were installed. And then following D line, E line, F line, and G line took the grout curtain down to elevation 0. And so that was just a sequence of all the grout curtains that the multi-row grout curtains that have been installed through the years. And then this is just a overview of the same information that was on the previous slide. You can see a lot more extensive grouting in the area here. Let's see if I can get my laser back. Oops. There we go. In this area, we have up to about 5 rows of grout curtain just in this section, and this is upstream of the 1968 sinkhole. And then this is a snapshot of the geologic model that Geosyntec has put together for us, showing this shows the extent of the depth of the grout curtain. And over here in the east, I'll show you this in the upcoming slides. This is a relatively recent addition to the remedial grouting efforts that we've been performing out at Logan Martin, where we're reinforcing the shallow epikarst of the rock out at the site. The goal with this phase of work was taken from a concept provided by William White and his literature, the geomorphology and hydrology of karst terrains. In that literature, he described the potential instability of shallow karst features with a varying water table. So as the water fluctuates up and down in these karstic features, it creates a suction that can, collapse the epikarst and lead to multiple failure modes. And the hydraulic conductivity across the site, the connection it has with the tail race, specifically the east embankment, makes shallow karst features susceptible to washout, losing its strength, and also susceptible to collapse, according to Wyatt's literature that we used as a basis of design for this work. And the goal with these columns is to, drill 50 feet into the epikarst and install, inject a volumetric limit of grout that gives us roughly about a 6-foot diameter column, 50 feet deep, and to help support the overburden directly beneath the embankment fill to help prevent the collapse. And now just a quick run through the geologic model. This shows where we've installed the columns to date. So right there where the columns are going up, that's the east bolster, the newly constructed east bolster. And then we had to recently raise the bolster higher so that we could get the sufficient spacing between the upstream and downstream columns. As I mentioned, the spacing we target is 20 feet. And what we found as we were drilling the east bolster was that the minimum rock cap that we needed for stability based on our calculations, we didn't meet that. And the rock cap that we were that we needed for sufficient support was 2 foot. And what we noticed in most cases was it was much less than 2 feet of a solid rock cap. In a lot of cases, that top of rock was highly fractured. So we had to reduce our spacing down with interspaced holes on roughly 12 to 14 foot centers. We notice the same thing as you go farther east as well, and that's part of the next phase of grouting is where we're going to install those new the interspaced holes where we had insufficient rock cap. Oops, let's back up one. Sorry, it took off on me. So another phase of grouting. Oh gosh, here we go. See if it stopped. Okay, I think it stopped. All right. Also, another phase of grouting that we're currently performing now, concurrently with the columns, is the I call it like a composite grout curtain. It's a combination of LMG grout, 2 rows, 1 row downstream, a row of LMG upstream. The goal being to target the large voids and karstic features that would be susceptible to having really high grout takes with high mobility grout, which is what we used in our conventional hanging grout curtain installation methods. So an effort to reduce, grout travel, like this section right here is roughly about, 1,000 feet, 1,000 to 1,200 feet from a weir that we monitor closely that's in the tail race. that flows roughly about 16 to 17,000 gallons per minute. We get grout travel that will communicate all the way, over 1,000 feet to that weir. And so an effort to prevent that grout travel and to establish more containment with our hanging grout curtain in this virgin area of untreated rock. It had been treated with the original grout curtain, but as I established, we've seen very little evidence that that original grout curtain is performing, is acting as a seepage barrier. I've cored a lot of holes out there, and I personally haven't actually recovered any of the original grout curtain. Although in other sections we have recovered traces of the original grout curtain, but I personally haven't in all the holes that I've drilled. But going back to this program, the goal is to establish containment in the more well-developed karstic features with the low mobility grout and come in between those two rows with our HMG grout curtain. We performed a proof of concept or a test section away from the embankment in an area where we had similar karst features. And what we were able to demonstrate with that proof of concept is a reduction of roughly about 30% reduction in total volume of grout. And that's considering the total volume from the low mobility grout and the high mobility grout phases of the work. So an overall 30% reduction in cementitious grout from a single line high mobility hanging grout curtain versus this three-phased multi-row low mobility grout, high mobility grout composite curtain. So one thing that makes Logan Martin, what I feel like makes Logan Martin extremely unique, is that we self-perform pretty much all of the work. The only services that we don't self-perform are consulting. As I mentioned, we have Geosyntec that's on board with us. We have a board of consultants, as well as Triel Engineering, another consulting firm that consists of Bobby Williams and Ron Robinson, which between the two of them, they have about 80 years combined experience at Logan Martin Dam alone. Bobby Williams was the previous geostructural services supervisor. There's not many people that understand and are as experienced in grouting karst as Bobby. And Ron Robinson, he's the geologist. Not many people understand the karst geology as well as Ron either, especially at a site like Logan Martin. So in addition to the 30% volume savings that we've gotten from this new composite hanging grout curtain concept, we've recently began a low mobility grout mix development program where we trying to get away from fly ash, because now fly ash is in low demand with fossil plants closing down one by one. And so in effort to get away from fly ash altogether and get away from our dependency on it, to keep our grout cost effective, we began substituting it, removing the fly ash out of the mix and substituting local clay, borrow material from here on site. Is everybody right now? Conrad asked if my slide stopped advancing. I'm on the slide right now with the equipment. In addition to the savings that we've had in grout, we also see roughly about a 50% savings in labor and equipment by self-performing. And in a lot of cases, I've seen pricing on other projects, and I kind of try to keep track of what the going rates are. And in a lot of cases, I see that we're performing our grouting programs much cheaper than, 50%, half of the cost of what, the typical contractor may cost. In some cases, it's by an order of magnitude of 10, just depending on the program. But so this is something that we've been able to achieve just because of the longevity of the project, from, having the project started all the way back to 1971. We've developed all of the experience and developed the skills internally with, we have our own drillers who are well versed in sonic, water hammer, air hammer. We have really good resources and really good experience in this project that allows us to operate the way that we do. So here's a couple other pieces of equipment that we have. As I mentioned, we sonic drill all of our production holes now. Here you got the our brand new TSI rig. This is a TSI 150C crawler out here farther along the east embankment. On the picture to the left, you can see the Borterra. Borterra is also shown there in the picture to the right, along with the two volumetric mixers. These volumetric mixers, they've saved us an extremely amount, of money. Originally, we got all of our low mobility grout from a local ready mix supplier, which we experienced just an extremely high amount of waste. The greatest addition we've probably had with equipment has been these volumetric mixers, because it's essentially cut our waste down to zero, essentially. This allows us to mix low mobility grout on demand, and also they serve as a really good emergency response piece of equipment. If we have, if there were to be a sinkhole develop, or if we're injecting with high mobility grout and we get into flow, these volumetric mixers can be utilized as a good emergency response to be able to mix low mobility grout on demand. So as I mentioned, recently we started this grout mix development program, testing our conventional type 1-2 cement mix, and also comparing that to our type 1L. And I also mentioned the purpose of this was to replace the fly ash and substitute it with the local residual clay that's processed from our local bar pit. And I'll just kind of highlight the high level results that we saw. There wasn't, we didn't really see any major changes, and I say major changes, and that's relative to the criteria that we need for the grouting that we're performing out there. We don't really need a lot of strength for the low mobility grout columns. Our design strength is 1500 PSI, and we were able to achieve that with replacing all of the fly ash and cement, what equated to roughly about 40% of the fly ash and cement content. So that means we replaced all the fly ash, and we were able to take some of the cement content, substituting it with the local clay material. And we were able to achieve, 1500 PSI, as you can see with this mix. And this mix 3 type 1L is the current with the super plasticizer, and that's the Sika 300 super plasticizer that we use with the clay mix. That's our current mix that we use for low mobility grout columns. Let's see. It's like it's not wanting to go. Let's see if I can get it. One thing we noticed is that the type 1L does gain strength a little faster, but it tends to have slightly less strength than the type 1-2. Some of that may be attributed to the first batches that came out of the local cement plant. I think they had a little bit of a quality control challenges early on in their type 1L deployment. They, according to our admixture rep, they were experiencing a little bit higher sodium carbonate levels in their cement, their type 1L cement, which acts as an accelerant. And so we were getting, I think that attributed to the higher strength faster, but it also attributed to issues with us, the grout flashing on us, which is why we had to revert to super plasticizer to help control the set. As I'm approaching, I think, close to the end, I'll kind of try to go through this last section briefly. If it'll go. Sorry, this is kind of freezing up because I have really slow internet here. So I do want to touch on the research and development program that we began back in 2000, and I believe it was 2016. We developed a test chamber for simulating karst geology in this test chamber, and then we use the mixed designs. We tested mixed designs that we've used in the project throughout the years, as well as we use this to help us develop and optimize mixed designs for future projects. And just a few years ago, we converted this test from what originated as like a static test, where we had this test chamber that we filled with geomaterial, like I said, to simulate karst, to now where we are, we modified the box, we reduced the size of it, and the setup now entails what we simulate is a karstic tube that runs down the length of the test chamber, and we introduce flow that goes from one end, unrestricted flow that goes from one end to the other. And then we grout through the side, intercepting the cross flow to determine which mixes are more effective at grouting off this cross flow condition that we sometimes encounter out at Logan Martin. And as you can see, the first set of tests that we performed went really well. This is a cross section, a cut section through the test chamber after the test had been completed and the grout set. We were able to achieve pressure in the chamber, grouting off the conduit pretty effectively. And this was grouted off with a 1-to-1 high mobility mix. You can say it was pretty effective. And with that, that's all I have, and that gives us, I think, roughly about 15 minutes for Q&A, which I think Kathleen is going to moderate.
Okay, thanks everyone. Great presentations. Appreciate the time that you put into them. We have a few questions, and Conrad answered a couple of them in the chat box. And Conrad, you said that you want to address the two questions that are posed correctly or in there now. So why don't you just go ahead and answer the two questions that are appearing in there. Everyone, I'm pretty sure everyone can read them, so I don't think I need to read through these. So Conrad, you want to answer those questions?
Sure. I think the one is the recording going to be available? I think so, but I'm not sure what the plans are there. So maybe someone from DFI or okay. So that one's good. The
recording will be available within 2 to 3 weeks from now.
Okay. And then the other one that's kind of still open, I think, is a pretty interesting topic of conversation, particularly for those of us in dams. So Adam Paisley's got an RCC job coming up, and he's inquiring about the the availability of C-150 cement in different parts of the country, and particularly kicked that to Jose. So Jose's got projects in this presentation that are from the Southeast, from Colorado, and from down here. We're practically on the border with Mexico.
Yeah.
And so if you want to just kind of relate what's gone on, and Sue had to go to 1L too, right?
We had to go to 1L as well. Yeah.
So
So, Adam, if I'm being completely honest, a lot of the jobs that, recent jobs that I've been on have asked for type 3 or type 5, or I think even Sulak was asking for type 3 for a little bit. It's not so much that they ask for type 1, 2 for the grouting. So I think the difficulty really for us has been who's still making type 3 and type 5. I see your point about the type 1 and type, you're still gonna make the type 1 to make the 1L, right? That hasn't really been the challenge necessarily. It's that a lot of specs. I mean, I was looking at a job in the Northeast, and it was asking for type 3. And like I feel like every spec I read for a new job that comes out asks for type 3. And type 3 is what I'm finding harder to find. When I was looking in Colorado, there was the company I was dealing with was like, yeah, we only have one plant that's providing type 3 right now. And I mean, you're lucky that it's close by. I think that's where I had most of, where in my experience, where we've had most of the challenges is the things outside of that type 1, that the type 1 C-150 mix.
yeah, well, I think one of the things we're seeing, right? So RCC job of particular interest. Are we live?
Yeah, you did.
But even though on an RCC job or a grouting job, right, you might use a ton of cement, figurative ton of cement, right? We use a tanker a day out here at Red Bluff pretty often. That's still a drop in the bucket compared to your conventional, other uses for concrete and ready mix and stuff, right? So, I mean, the reality is as a designer, you just kind of have to figure out your local market and have an idea of what's going to be cost effective and whether you can live with it or not. Because if you spec something that's not commercially available, at the very least, it's going to be very expensive, and at the other end, you just can't lay hands on it at all. So I think it's a challenge for the designers and the contractors right now. And then I think one other thing we found at Red Bluff, right, the 1L here met the type 5 sulfate resistance that was in the spec. And so that's how it was a relatively easy, straightforward thing. In the answered column, I copied and pasted in Josh Gilman from the Portland Cement Association's response about kind of the extra designations that may be appended to type 1Ls as you're looking at products, either to spec them or to buy them for building something. And there are extra kind of nomenclatures on the products to indicate, which capabilities a type 1L cement or 1P or whichever they are, what they've got that would match something from a 1, 2, 3, 4, 5 cement that you've seen in the past. So just, I'm not sure if Josh can speak since he wasn't a panelist, but I do want to make sure, that his extra information was available there to everybody.
Yeah. I don't know if there's any more questions.
Actually, I have a brief question for Eric. In Jose and Conrad's presentation, they had included the percentages in the type 1L in the testing that they had done. Do you know what the percentages for the limestone is in the type 1L that you're using at Logan Martin?
It's 12.
Thank you.
Yep, 12%. And one of the testing that we're going to do in the test chamber in, I think, April or May, whenever things warm up in Massachusetts a little bit, we're going to test. And one thing I might like to do is maybe test some of those type 1L cements that Conrad and Jose have experience with, and compare the different limestone content with each other in our test chamber, see how they perform in rock grouting.
Thank you. So does anyone have any other questions to ask, to pose to our presenters before we close out our webinar? Going once? Oh. Okay, so I would like to thank everyone for calling in and participating and attending our webinar today. I would like to again remind you that our next webinar will be in July of 2025, and the information on that will come out at a later date. And also, if you are interested in joining the DFI International Grouting Committee, please let us know. We are welcoming members at any time, and you know, the more communication that we have within the industry, I think the better off, you know, the industry gets. So again, to remind you, the week of April 28th, DFI will be holding their DFI committee week, and the schedule for that will be coming out soon. So please, if you can, if it will fit your calendars, please call in and attend the meeting that we'll be holding for the International Grouting Committee at that time. So with that, I'd like to again thank you to all of our presenters for taking the time to put together the presentations and to spend the time letting us know the things that you're doing out there in the field. So thank you very much. We appreciate everybody's attendance, and have a great holiday. And with that, we'll conclude our webinar. Thanks again.